All right, everyone. How's it going? We're going to jump to the next section, which is on hyperbolic functions, and this sounds pretty cool, right? Hyperbolic functions, and these functions are really cool. So, let me give you just the first one. So, they have an association to the standard trigonometric functions like sine and cosine and things like that. And so, the very first one we'll talk about is this. Okay, so maybe I'll put the parentheses for clarity is sin, so sine h, so the h is for hyperbolic of x. So these four letters constitute the function. So this is defined as the following. So you read this as, so this is read as hyperbolic sine. So that's how you read this. And then some people also call this, just for short, they call it cinch. So maybe I'll just like try and spell it cinch like that, S-I-N-C-H. But I prefer hyperbolic sine, but you know, it's up to you. You kind of, this is a mouthful, so cinch is very quick. And so they're defined more or less kind of in this rough manner is, you know, you have some combination of e to the x or e to the minus x. And at first this may seem, you know, kind of strange and artificial, but these functions show up a lot in engineering, physics, and other applications. They kind of like, I know for sure since I studied physics in undergrad, I know they come in modeling like the absorption or the re-emission of light, or they kind of like model the behavior of light in certain conditions and stuff like that. Maybe more to the real world is they also describe water waves. So the book has a nice picture of this. Let me maybe try and emulate it. So say you got your water wave here, and so you define, and this is like the bottom of the you know, the sea at this point, whatever the ground is, the bottom. So if you call this distance d, so the distance to like the water wave, and then maybe I should draw this a little better. So this wave, you're thinking of it as like a wave that's periodic, so it repeats itself. So the distance d is this, and the length of the wave is basically like what we thought of as like the period of a wave. It's like the distance from one crest to the other. So if you have a water wave traveling like this, actually its velocity is modeled by this formula. It's equal to the square root, this guy here, and then this function that I haven't talked about yet is hyperbolic tangent, so tan h. I don't think this one has a short version like cinch or whatever. If there is one, I haven't heard it, or maybe I forgot. But yeah, this is hyperbolic tangent. So notice the velocity of this wave that's traveling, this water wave, is more or less described by this tangent h. You need the hyperbolic tangent function to describe this. There's also other things that we can talk about in class, but the idea here is that these functions show up as models of a lot of phenomena in life, so that's why they get a whole section dedicated to them. So they're very interesting and neat. The next up is if we had hyperbolic sine, we should have hyperbolic cosine, and the only difference is here there's a plus sign. Only a slight difference. And then last, not last, but you know, in trig, sine and cosine are the most important things. Everything else comes from those two. And it's the same thing here. Hyperbolic tangent is the ratio of hyperbolic sine to hyperbolic cosine. Just how like regular tangent was sine over cosine, this is sine h over cosine h. Oh, and then some people call this thing cosh. So some people like to call this cosh, like C-O-S-H. It sounds kind of interesting to me, but yeah. So that's also called cosh or hyperbolic cosine. And so if you do the algebra here, if you take this thing and you divide it by that thing, you end up getting that's what you get. So hyperbolic tangent looks like that. And then, you know, the other three, you know, cosecant, hyperbolic cosecant is now the same way as regular cosecant. It's basically the reciprocal of this. So it's 1 over sine h. And hyperbolic secant is 1 over cosine h. And hyperbolic tangent, or sorry, hyperbolic cotangent N looks like an H, is the reciprocal of hyperbolic tangent. So yes, we have all of these guys here. Let's put a dot. So these 6 are, instead of the trigonometric functions, they're the hyperbolic functions, but you can see that they match there's a large parallel to these and trigonometric functions. A very large parallel here. Okay, and then let's see what the graph of the main 3 look like. Let's just focus on the first 2 for a second. And this is like a rough qualitative thing. We'll do a few calculations of points. So actually, let's just leave room for the first one. So hyperbolic sine. Let's see what hyperbolic sine of 0 is. So you're going to plug in zeros here. Well, this is just 1. Negative 0 is still 0. Right? So then you get 1 again. So this is 0. Okay, so this function goes through the origin, basically. You know that hyperbolic sine passes through this point. That's good to know. And then if we rewrite this as like 1/2 e to the x minus this guy, then we can kind of see the behavior of the function for large positive values and for large negative values. What I mean by that is if you look at this limit, okay, notice that this thing will go to 0, right? Because if you plug in infinity here, we get e to the negative infinity like we talked about, that's 0. So this thing is going to approach essentially what the function 1/2 e to the x looks like for large values, which gets very large, but it roughly looks like that function. So it looks like this for large values, like 1/2 e to the x. And then you can imagine what happens for negative values as the exact opposite. So now, negative infinity here will make this go to 0. And so this guy looks very similar to this function, which without the negative 1/2 in front, for very large negative values, this guy normally goes up to positive infinity, right? E to the negative x looks like this normally. So for negative values, it shoots up. But this minus 1/2 is going to flip this. It's going to make this go in the negative direction. Okay, and so this guy will actually shoot down to negative infinity. So it looks like roughly like this. It has a there's like a small bend here. There we go, that's better. So this is what sine h looks like. Maybe I should put it in a different color. So hyperbolic sine looks roughly like this. And now let's do hyperbolic cosine. Oh, sorry. X is just this. Okay, and then, so yeah, let's plug 0 into this guy. So you get e to the 0 plus e to the 0 again over 2, because negative 0 is the same as 0. So now you actually get 2, or 1 plus 1 over 2, which is 1. So this function does not go through the origin, it goes to the point 0, 1. So actually the graph looks more like, that point looks like this. So at 0 units, you're 1 up. So the function goes through there. And then blue, sorry. And then we can kind of do the same thing in terms of the behavior of this guy. Okay, so now notice this minus sign is not there. That's the only difference. So for positive values, we're going to get the same outcome as with hyperbolic sine. Because, you know, when you go to positive values, large positive values, so this guy, this thing dies out. This goes away, and then this gets very large. And actually, the larger numbers you stick into this, you know, if you stick positive numbers into this guy, e to that larger number is going to be a bigger number. So this function only grows. It never goes down, at least for positive values. It doesn't for negative values either, but that's all we've discussed. So this thing from this lowest point basically just shoots up to infinity. And actually now you can see if we do the negative infinity here, just make a small difference here. Now this guy will go to 0 like we talked about, but there's not that minus sign here now. So what we get is that you get 1/2 e to the negative x, which if you plug in very large negative numbers into this is going to be like 1/2 e to a huge positive number. Huge positive number. So this will also go to a very large positive number. And it looks like this. So this is hyperbolic cosine, graph of that. And then last but not least, hyperbolic tangent. So we have an explicit formula for it. We have that. What is it at 0? Okay, so it's e to the 0 minus e to the negative 0. So this, like we talked about, is 1 minus 1 all over 2, so this is actually 0. So hyperbolic tangent goes to the origin. And then now it's kind of interesting to see what the behavior for large values is. So, you know, normally if you just like plug in infinity, you're going to get like some problems. So we're going to do a standard trick, right? If you just plug in infinity here, you get like e to the infinity, e to the negative infinity, e to the infinity, to the negative infinity, which these guys go to 0. But e to the infinity over e to the infinity gives like this weird infinity over infinity problem. We don't know if the top wins or if the bottom wins. And actually this is something we're going to talk about in the next section is L'Hopital's rule. Kind of helps us deal with this in a systematic way. But we don't need to resort to that. We can use the same idea that we have before, is multiply by the thing that's like the biggest. So normally when we have like polynomials like x squared plus 4 over x cubed plus 7, and we wanted this limit, you multiply the top and bottom by 1 over the highest power. Essentially you divide each term by the highest or the biggest term. In this case that's e to the x. So if we do that, if we divide each term by e to the x, aka multiply the top by this and the bottom by that, this ends up being 1 minus e to the negative 2x over 1 plus e to the negative 2x. And now our problem suddenly disappears, because if you take this limit now, you can see that this will be like 1 minus negative 2 times huge number. This essentially approaches negative infinity, and same thing here. So this approaches 1 minus 0, 1 minus 0, which is 1. So this approaches 1 in the positive infinity case, and if you work it out for negative infinity, it will actually approach negative 1. So the graph kind of looks like tangent inverse a little bit, the graph of tangent inverse, except it has different horizontal asymptotes. So now 1 and negative 1 are the horizontal asymptotes. The function kind of looks like this. So this is hyperbolic tangent. Okay, and then you could do this, for the other ones as well, but we don't care too much about. We do care about them, but they're easily understood after we know these. And now there's some cool things, again, more parallels between hyperbolic functions and trig functions, namely that the hyperbolic functions you expect to be odd or even are odd or even. But what I mean by that is, remember, sine is an odd function, and actually hyperbolic sine is also odd. So this is basically telling you hyperbolic sine is odd. That's literally what that means. And then hyperbolic cosine ends up being even, and again, you could have seen these from the graph. When we graphed this, because of the symmetric properties that they had, you could have saw this as well. Okay? And then as a consequence of this, hyperbolic tangent is odd. If you take an odd function and you divide it by an even function, you get an odd function. And maybe that's a good problem for us to think about in class. Why is that true? And the rest you can also work out that way. Okay. And then another really cool parallel is this one. Actually makes a lot of sense, and if we think about it first in terms of the circle. So remember, the sine and cosine were defined on the unit circle. What was the unit circle? It was a circle with this equation, aka circle of radius 1. And what sine of theta and cosine of theta represented, what these functions were defined as, literally meant if from the positive x-axis you go theta degrees or radians or whatever measure you want to use counterclockwise, and from the origin you draw a line until it intersects the circle. If you look at this point here, okay, this angle is theta, this ordered pair here is just some arbitrary point x, y, right? I mean, that's what anything in the plane is. But what sine and cosine are, they're literally the functions that tell you what x and y are. They tell you how far to the right and how far up to go. You know, it could be down or left, depending on where you're at, but in this case, it's right and up. So literally, that's what the function sine and cosine told you. They told you the x and the y coordinate. Oh, sorry, I haven't flipped. Cosine tells you the x coordinate, and sine tells you the y coordinate. Okay? So that's how these functions were defined. Now, because of that, notice if you switch x with cosine as it should be, and y with what it should be, you get the famous identity cosine squared plus sine squared equals 1. Okay. Now for hyperbolic functions, what shape do you think is the one we're going to consider? You guessed it, it's the hyperbola. So if you think about now, instead of the standard hyperbola, which minute difference is x squared minus y squared equals 1. So instead of a plus, there's a minus. That small difference changes the shape that you have drastically. So instead now, we have the hyperbola like this. And what's interesting now is if you take this point here now, similar to sine and cosine, it's related in the same way. You know, if you consider just like, in this case, angle may not make as much sense, you know, but just some real number that you stick into the function. Because an angle is just a real number, right? So if you consider it like that, as just some real number that you're using to measure something, like in trig world it was the angle, then this point here is hyperbolic cosine of, we'll just say x. Maybe x is confusing because that's like an xy pair. So let's say t. So the xy coordinate on this hyperbola now is going to be given by, the x coordinate is given by cosine h of t. The y coordinate is given by sine h of t. So that's really cool. And because of that, again, if you let x be this guy and y be that, then you get a very similar result, as you get that cosine h squared was 1. So minus. That minus sign is all the difference that it takes. And you get a drastically different shape. So that's pretty cool. So that's one property. And then again, there's other properties that you can work out that are similar to trig, but we can talk about that more there in the book. And then, so yes, I think now that we've talked about, you know, what the heck these guys are, what they mean, kind of where they come from, we can, you know, do what this class title is do some calculus now. So the question is, what is the derivative of these hyperbolic trig functions? So what is the derivative of hyperbolic sine? Like, what the heck is that? Actually, this is not too bad, is because, you know, we know an explicit formula for this. It's the easy way is the 1/2 e to the x minus 1/2 e to the negative x. Remember, this is the same thing as what I wrote down earlier. These two are equal. But this one just looks so much nicer because now you can just take the derivative more quickly. Okay, so the derivative of this will be, well, this guy doesn't change. And then, or let me maybe put this in steps. So remember, the derivative goes to each piece. Okay? And then in the eyes of the derivative, remember, constants were irrelevant. Same thing with the integral, right? You can just pull these 1/2 in front of the derivative. Okay. Now the derivative of e to the x is amazingly itself, so this guy doesn't change. And then this derivative is almost itself, but remember, because this is not x, it's minus x, we have to use the chain rule. So the chain rule says you take the derivative of e to whatever you covered up as normally. So the derivative of e to anything is e to that same power. So this will be e to the negative x, but the price we pay from the chain rule is you have to multiply by the derivative of the thing you covered up, the thing that is not x essentially. And this is just -1. So this multiplies a -1, which will actually just turn this into a plus. And then now if we rewrite this in a more familiar form, and remember, this is actually hyperbolic cosine. And again, this is another parallel to trig functions. Remember, the derivative of sine was cosine. That's kind of interesting. And the derivative of hyperbolic sine is hyperbolic cosine. So well, let's write that down now. So that's one derivative. And then the other one, of course, if you did sine, you got to do hyperbolic cosine. And this one actually doesn't introduce a minus sign. So normally the derivative of cosine was negative sine, but here you actually don't pick that up, which is really cool. I'm trying to think. This has a very strong physical reasoning for this, or has large physical implications. Because notice now, hyperbolic sine or hyperbolic cosine, if you take two derivatives of either function, you get back to the original function. So one derivative of this gets you cosine, one more derivative gives you sine, or vice versa. One derivative of cosine gives you sine, and then one more derivative of that gets you back to the original thing. And so if you're looking for functions whose second derivative is equal to itself, or maybe some constant times itself, hyperbolic sine and cosine are the answers to that. They're functions that have this property. And you may think that this is a very artificial type of scenario, but actually almost literally every equation in your introductory physics class and many other physics courses are in this form, because Newton's second law says that force is equal to mass times acceleration, but remember, mass was a second derivative. Acceleration was a second derivative. So now if you move this over, you have that this quantity force is your mass times acceleration, and notice there's a second derivative here. And many times the force is proportional to that acceleration. So for example, in Hooke's law, it says if you have a spring attached to a mass, and then you pull on this guy, the force that the spring is creating in the opposite direction is proportional negatively, right? Because if you're pulling to the right, the force should go to the left to this to the acceleration. So Hooke's law is, you know, F equals negative kx. Sorry, not the acceleration, the position. So the position of this, so the more you pull this to the right, the larger the negative force should be. So see this x, the larger x gets, the position of this. This right here is x equals 0. So this is x is 0 right now. But if you pull this more and more, the force going in the opposite way is negative, is proportional to how much you're pulling it. And this k here is called the spring constant. But notice that this tells you, since this is a force and F equals ma, look, if you divide by m, you get negative k over mx equals x double prime. So you have the solution, the answer to, you know, this equation here is what function satisfies this. And you know, if you know the function x, you would know the motion of the spring. Because if you knew what x as a function of time was, you would know where the spring is going. And the answer to that is these kinds of functions, because they have this exact property, is that their second derivative is some constant multiple of the original function. And so yeah, hyperbolic sine and cosine can model a lot of stuff, like, and maybe you could just see that already, but that's just a little side note right there. Okay, and then we have the derivative of hyperbolic tangent. That's going to be, surprise, surprise, not really. It's hyperbolic secant squared. So again, that's very parallel to the other one. And then we might as well put the other ones. So again, it's negative cosecant cotangent, but notice this is cosecant h, so hyperbolic cosecant, and cotangent h, so hyperbolic cotangent. That's pretty interesting. And then the one for secant is, again, normally the derivative of secant is secant tangent, but now they're just hyperbolic secant and hyperbolic tangent. And then normally the one for cotangent was negative cosecant, and this is again negative cosecant h squared, so hyperbolic cosecant squared. So that's pretty interesting. And remember again, as in trig, this notation here, this literally means the function, you get whatever that output is and you square it. So you stick a number in for x, you get that number, and then you square it. That's the answer to this. That's what this means. Okay, so those are the derivatives of our hyperbolic trig functions. And then because these are, they're functions, one would hope that they also have inverses, and they do have inverses. And so the three main ones that we care about are the ones for sine h, cosine h, and tangent h. And so the inverses exist. And they're actually given by a specific formula. You can actually solve for the formula. So inverse hyperbolic sine is given by this. And at this point, this is just a collection of random facts. It's just these functions are so useful that people have established these things about them, and they're just used here and there randomly. Okay, and then this makes sense for any x, real number x. Right, I can stick any number x into here. The issue with the square root is gone because you square the number, meaning it can never be negative, so you're good. And then inverse hyperbolic cosine is given by this. Okay, so minus sign here now. And now you can see that this does bring some issues up. So actually this is for any x 1 or larger. So we have to make that condition. And then last but not least, the inverse of hyperbolic tangent is, again, you probably might have guessed what this should be. It's somehow related to these two. And then this is for x basically in this interval, meaning x is a number between -1 and 1, but it can't be those because these are not less than or equal to. So it's some number between -1 and 1. That's the definition. And so, yes, we can get corresponding graphs for these guys and so on and so on. So we can, we can graph these and plot them, but we might just look at that in class just so we have more time to do some other things. Okay, and then similarly, if you got these guys, you'd like to know their derivatives, right? So we can get the derivatives of the inverse hyperbolic functions. And yeah, as you can tell, even I don't necessarily remember these right off the top of the bat, unless you've been working with them, the past couple of days, and you remember, you might have to look these up. But the idea is that they exist, and we know what they are. So they exist, and we can find them. So, I forgot the inverse here. But so now we have a large new collection of derivatives because we have a lot more functions. Now we have the 6 hyperbolic functions. We also have the 6 inverses of the hyperbolic functions. So this is crazy. We're getting all these new functions and their derivatives. Okay. And so let's see. Let's do one example now. Finally, we can do some examples. So let's say you want this. Say you want the derivative of this guy. Okay? So it's clear that we need to use the chain rule, right? Because this is not just x. So we know, let's recall what just the derivative was when it was x. What was it? It was 1 over 1 minus x squared. Okay, so using this fact, we know that this should be 1 over 1 minus this guy squared, which we'll just write as sine squared x. But because of the chain rule, we have to multiply this by the derivative of the input, basically, sine x. And then, this is just cosine, so we have times cosine x. And then, you can think of this as divided by 1. So you get cosine x over this guy. And then I'm wondering if they do simplify it more. Okay, so then if you remember, since sine squared plus cosine squared equals 1, if you subtract sine squared from both sides, you get that cosine squared is actually 1 minus sine squared. So this is cosine x over cosine squared. And if you don't remember this, that's fine. I don't want to get too into the trig stuff. But you'll lose 1 cosine here and keep 1 there. And then 1 over cosine is secant x. Which this is really interesting now, because look what this means. Is we know this is equal to secant x. And so remember, if you take the integral of both sides, cancels out here, and we get that. So we just now know what the integral of secant x is. So the integral of secant x is this really strange looking function. That's pretty cool. Because normally we only knew the integral of secant squared. If this was squared, the answer here would be tangent. But just secant, well, you get this weird complicated looking thing. So, I mean, that's pretty crazy how the squared changes all of that. So that's pretty neat there. And then, yes, you guessed it, that like all these properties here will probably help us do certain integrals now. And the answer is yes, they will. So let's say we want to find this integral. Say you want this. And recall that in a similar fashion, the derivative here was that. And so meaning again, if we take the integral of both sides, cancels out here, right? Integral and derivative cancel out. So you know that the integral of this guy is just sine h. So this just becomes sine h x evaluated from 0 to 1. Okay, which is just sine h1 minus sine h0. And we've already seen that this is 0. But let's see why again. So remember, sine hx was this guy. If you plug 0 in, you get e to the negative 0. So e to the 0 is just 1, right? So 1/2 times 1 is 1/2. And then, negative 0 is 0, so you get the same thing here. So that just gives 0. So this piece is 0. and we're just left with sine h of 1. So then now let's find what sine h of 1 is. It will be 1/2 e to the first power minus 1/2 e to the minus 1 power. And so if you write this, this is like e divided by 2 minus, remember e to the negative 1 is like 1 over e. So this is like 1/2 times 1 over e. And so this combines to 1 over 2e. So you can leave it like that. I'm wondering, oh, and I see something that I'm doing wrong, is I have sine h the whole time. This should be sine h inverse. I'm so sorry. It should be sine h inverse. So actually, let's recalculate this. I guess it didn't hurt to do this just for practice, but this is not going to be the right answer. As the inverse, I'm so sorry. So sine h inverse, remember, was supposed to be ln of x plus, it's supposed to be this. So what is sine h inverse of 0? Okay, well it's the ln of 0 plus 0 squared plus 1, which when the dust clears, this is just ln of 1, which we said is 0. So actually that matches. So this actually is also 0. Lucky guess. And then sine h inverse of 1 would be the ln of now 1 plus 1 squared plus 1. So this is the ln of 1 plus root 2. So when the dust clears, this is the final answer. Now let's maybe do some more practice with some of the homework problems. Okay, and I know that integrals are definitely a little more challenging than the derivatives, so maybe let's do some of the integral problems. So this is 61. So we have integral of sine h of root x. So you know, you can write these parentheses if you want, if you don't want to, and it makes sense what this means. You can omit them. So I have that. Now, okay, we have certain options. And if you sit there and think long enough, the choice of u that you want to make, you might think it'll be root x. That's what I'm thinking. Let's see if it's right or not. So remember, you take the derivative. So you get du, and remember this is like x to the 1/2. So its derivative is 1/2 x to the minus 1/2. And this derivative happens so often that you might remember its alternate form. Is remember 1/2 x to the minus 1/2 is 1/2 times 1 over x to the 1/2, which is 1/2 times 1 over root x, which is 1 over 2 times the square root of x. So this is a nicer form. But remember, we have to tack on this dx here. So you might literally remember this because it just happens so often. So this is, this will be 1 over 2 root x dx. And then if you multiply both sides by 2 root x, you get this. And this is why this choice was nice, because notice that this root x will cancel out with that, because dx gets replaced with this. So now we have the integral of sine h of u. This is the root x we want to replace. You know, technically, you could let this be u, but that's not the u that's not the root x that's going to work. It's kind of weird. If you change this to u, none of this would not work out so nicely, because this root x is trapped inside the sine h function, but this one is free. So we get sine h u over, we'll keep this one root x, and then dx is 2 root x du. And so very nicely the root x's cancel. And then the 2 is a constant, so it floats in front of the integral. And now you may think, what's the integral of sine h? We never talked about this. Well, we've done this so much, I think the book kind of wants us to come up with these answers at this point, which is not bad, because if the derivative of cosine h, as we saw, was sine h, then the same idea that we've done a lot applies. You take the integral of both sides, cancels out here, and this means that the integral of sine h is cosine h. So we do know the integral of sine h. It's just cosine h. So this becomes twice cosine h of u plus c. And then when we substitute, remember u was root x. Cosine h of, and that's our final answer. Okay, so that's pretty neat. And let's just keep trekking on. Let's just keep doing this. So we'll just go to the next problem, which is 62. And this one asks the integral of tan h x. Okay, and remember, there was nothing whose derivative was tan h, right? If we had the derivative of something equal tan h, we, by the same process that we talked about when you took the integral of both sides, would then know, because this cancels out here, we know that the integral of tan h would be equal to whatever this was. But there's nothing like that. There's nothing that was just straight up tan h. And so this is not as easy as it looks, I guess is what I'm saying. So let's maybe think about rewriting this as sine h over cosine h. And now you might know exactly what to do. So the choice of u is definitely either going to be this guy or this guy. But remember, you divide by the derivative of what u ends up being. And so the dividing action will take care of this guy. It will not take care of that. So we should get rid of this, meaning that this should be u. And then remember, du then would be the derivative of this, which is just sine, not negative sine. And so du divided by sine h is dx. Okay? So now we have the integral, and then this is u, and then dx gets replaced with this. And lo and behold, they cancel here. So then we get the integral of 1 over u, which is a very nice integral. We love this. It's, remember, the ln of absolute value of u. And then what was u? It was cosine h. So this is ln, the absolute value of cosine h. But if you remember what the graph of cosine h looked like this. This had never a negative value. So no matter what x I stick in here, and I calculate the output, which is this number here, it tells you how high to go. This is cosine hx, that height. That height, which is essentially what this is, for that choice of x, is never negative. Meaning you could just drop the absolute value symbol. Had it been negative, you would have to always been negative, you have to just tack on a minus sign. So if you want to drop the absolute value on something that's always negative, you pick up a minus sign, but here you don't pick anything up. So you get that. So that's pretty cool too. And then now, let's see how we're doing on time. Okay. So now here's another one. Alright, how about we jump to 65? I think this is a better one. So we're going to jump to 65 just because it kind of is a little different than what we have been seeing. So this kind of looks like it should relate to the inverse hyperbolic functions. In particular, if you look here, the derivative of hyperbolic cosine inverse was this. Ended up being that. So this kind of looks like in that form, right? It's something squared minus a constant. Granted, that's not 1, so we'll have to think about maybe how to correct that. That's the key here. But remember, again, this is so nice. We're doing this so many times. As if you take the integral of this tells you, because this cancels out, so you just have integral of this equals that. This is the thing that we're going to use. So what we're going to do is let's factor out a 9 here. So let's pull out a 9 out of this integral. Or sorry, out of the square root thing. So remember, if you factor a number out, you end up dividing each term by it. So when you pull the 9 out of here, you get t squared divided by 9, and then here you get 9 over 9, which is just 1. And the reason why you divide by it is because, remember, if you distribute this number that you factored out back, which is a multiplication, you should get this. And so division and multiplication undo each other. So see, if you distribute the 9 here, you get t squared, and then the 9 there, you get minus 9. Okay? And then what's nice about this is that this 9 pulls out of the square root now as a 3. So you get a 3 here, and t squared over 9 minus 1 Okay, so this 3 is just a constant. Now we don't care too much about it because constants don't really do much in integrals. They just float out in front and then multiply the final answer. Now you might be like, okay, you got the -1, but now you don't have it in the term x squared. But we kind of do. We have something squared, right? If you think about this, you can think about this as t over 3 squared so it is something squared, right? It's something like that. It's something squared. And so this is, we're getting close. So you can see how maybe it'll do this. But the way we formally want to deal with this is basically you can just use u substitution. So what we're going to do is you're going to let u be equal to t divided by 3. Because, right, this is t over 3 squared, right? So you're going to let u be t over 3. And then what is du is going to be just 1/3, right? Because t over 3 is 1/3 t. So the derivative of this is just 1/3. So now this is 1/3 and then dt. So then 3 du is dt. That's what dt will get replaced with. So all that happens is that this becomes u squared, and dt just becomes 3 du. Actually, look, the 3 cancels out. That's pretty cool. Okay, so the 3 cancels. I don't want to erase our integral, so maybe we'll go here. So then we end up just getting, and these limits of integration, I'm just going to keep them because we can substitute back at the end. So I'll just keep the limits of integration. Technically, because we did u substitution, you would have to change them, but I'll just keep them. And so this becomes okay, and then notice that's exactly this, except for u's. So this becomes hyperbolic cosine h inverse. So hyperbolic cosine inverse of what was u? It was t over 3. And then we evaluate this from 4 to 6. So pretty crazy here. Okay, and then at this point, this, we kind of just know that we know the formula for cosine h, so we can put it in there. I'm trying to see if we have time. We do not, but this would effectively be 6 over 3 is 2, and then 4/3. And then we have that explicit formula for what the inverse hyperbolic cosine should be. It's this guy. Right, so you would just plug this in, and that's, this is just arithmetic at this point. So the key part was the calculus. Okay, and then I'm sure we'll have a lot to discuss about on this in class. So hopefully this gets us started.
Okay, I'll see you guys next time.